So this video is part 3 of section 7.2 volumes. And what if a solid isn't generated by revolving a region around an axis? Okay, so I take us back to the pictures that I showed you at the beginning of the lesson of these three-dimensional figures that you are familiar with their formulas for volume, right? And we talked about where if you know the area or how to calculate the area or what the area is of each cross section, then you just end up multiplying by whatever the height is here. Okay, but it gets a little bit tricky and we end up needing calculus if the area of each cross section is not the same. Okay, right? Like we started talking about like, well, what if we wanted to calculate the volume of a loaf of bread? And we talked about how we could estimate by taking a finite number of slices and finding the volume of each slice and then adding those slices up. And that would be an estimate, kind of like when we were using rectangles, adding up the areas of rectangles to estimate the area under a curve. And then we came up with the idea, well, what if we were adding up the volumes of infinitely many cross sections? And we came up with the method of washer method and, disk method first and then washer method for coming up with the area of regions that have created solids that have been created from regions being rotated around an axis, right? When there's always a disk, either a disk cross section or a washer cross section. And then we ended up integrating the area of the disk, right, on the interval from A to B, or we were integrating the area of the washer on the interval from A to B, right? And then integrating with respect to X or Y, depending on whether we were thinking about taking vertical slices for cross sections or horizontal slices for cross sections. That is the same idea. So I'm revisiting our volume definition, and disk method and washer method is really just specific cases of this definition of volume, right? Like we're thinking about adding up the volumes of infinitely many cross sections in order to calculate the volume, where dx represents the infinitely small width of each of those cross sections, or dy as well. It would be the width of the infinitely small cross sections. So we're going to talk about a new type of solid that can be created when you know the shape of the cross section and you can determine you can come up with a formula for the area of each of those cross sections, thinking about the given region as being the width of the base of whatever the cross section is. So let's get into this first example. So imagine the base of a solid is the region in the xy plane bounded by x equals to 4 minus y squared and the y-axis. So that's a parabola that opens to the left. So this would be the base of the solid, which is this sideways. Sorry, I'm not doing a good job of staying in the lines. This sideways parabola here. And then the three-dimensional solid that has been drawn has been created by thinking about the cross sections as being squares that are perpendicular to the x-axis. So one of those squares has been drawn, but there are infinitely many squares. You could think of it like a stack of paper, right? Where each cross section is super thin, like a piece of paper. But the width of each cross section is this distance. So from the top of this sideways parabola to the bottom of the sideways parabola would represent the width of the square cross section, right? And then it comes up. So the area of each cross section is going to be dependent on x. So in order to come up with our volume formula, which our cross sections are perpendicular to the x-axis for this first solid. So that means that we are integrating with respect to x. I'm looking at the base of the solid is defined from x equals to 0 to x equals to 4. So those are going to be my limits of integration. And then we need to figure out how to represent the area of each cross section, right? With respect to x. Well, a square has the same length sides, right? And the base of each of these squares is going to be dependent on x as well. So we can come up with a statement, a mathematical statement to represent the width of each of these squares, the base of each of these squares. So we could say that s of x is equal to, well, we want the width to be in terms of x. So why don't we solve this equation so that we can figure out what y is equal to at this point on the parabola, as well as this point. So if we solve for y here, we would subtract by 4, and then we would have negative y squared, and then we would think about dividing by negative 1. So we would have plus or minus the square root of 4 minus x is equal to y. So the top part of the parabola, the top part would be y equals to the square root of 4 minus x, and then the bottom part would be y equals to the negative square root of 4 minus x. So thinking about how to come up with that distance, this is similar to coming up with the radius of rotation, right? It's going to be top minus bottom. Oops. So we would have the square root of 4 minus x minus negative square root of 4 minus x, which that would just end up simplifying to be 2 root 4 minus x. And like I said, area of a square, since squares have the same side lengths, that means that each cross section that is a square, that doesn't look like a square, would be a length of s of x. So the area will be s squared, or s of x squared. So that's what we're able to integrate here. Area, I could say a of x is equal to s of x squared. So then we're integrating from 0 to 4, s of x squared dx. And s of x, I guess I could have just, here I'm just going to write what s of x is equal to, is 2 root 4 minus x. So simplifying that, that'll be 4, which I can pull out the 4, times the integral from 0 to 4 of 4 minus x dx. And then integrating, that'll be 4x minus x squared over 2 from 0 to 4. And then if you apply first fundamental theorem of calculus, this ends up being 32, but you can check my arithmetic. Now the second part of this question says, find the volume of the solid where cross sections are squares that are perpendicular to the y-axis. So we don't have the picture of that solid, but we could figure it out here just to make life a little bit easier. I'm gonna delete that. Okay, so let's think about having cross sections that are perpendicular to the y-axis. So let's say we're taking one cross section is perpendicular to the y-axis. So it has a width from the y-axis to this point here on the parabola. And then since the cross sections are squares, that means that the cross section would come all the way about up there. Right? So this would make a very different looking solid. Okay, so let's say that that's one cross section. Now the width of that cross section using the base, so S of y in this case, well, if we think about right minus left, that would just be 4 minus y squared minus 0. It's up to you if you want to put the minus 0. And then again, thinking, okay, well, a of y in this case would be S of y squared, right? The area of a square. So volume of that solid would be the integral, and reading y values, okay, well, if we let x equal to 0, the y-intercepts would be -2 and 2 for the base. So we're integrating from -2 to 2. Four minus y squared dy. And when we integrate that, we will get 4y minus y cubed over 3 from -2 to 2. Then, oh no, I forgot to square it. Sorry. S of y squared. Okay. So that needs to be multiplied out before we can, because I'm tired, you guys. I'm sorry. U substitution would not work in this case. We do have to multiply out. When that is multiplied out, that's 16 minus 8y squared plus y to the 4th dy. And then we can integrate. Now we're ready to integrate. So is that minus 8/3 y cubed plus y to the 5th over 5 from -2 to 2. Once you apply first fundamental theorem of calculus, so that evaluated at 2 minus that evaluated at -2, you should get 512 over 15. So you can double check that that works out. Okay, for this next example, we are going to find the volume of the solids, and I'm not really concerned with coming up with the actual value. The hardest part, I think, is setting up the integral that represents the volumes. So that's what we're going to do for each of these. But we're going to set up the integral that represents the volume of the solids whose bases are bounded by the graph of y equals to x plus 1 and y equals to x squared minus 1. So I think it does help to draw the picture. Okay, so x plus 1, that would be the line that would have a y-intercept of 1 and a slope of 1. And then x squared minus 1, that's x squared shifted down 1 unit. Okay, and has x-intercepts at 1 and -1. Okay, so this is our region that represents the base of the solid that's going to be generated. Or many solids are going to be generated just using different cross sections. Now, all of the cross sections are going to be perpendicular to the x-axis. And we need to figure out what interval it is that we are going to be integrating on, right? What x interval we're going to be integrating on. That'll just be looking at the points of intersection here, right? So the first one we can see is at -1, 0. Now you could figure that out, just your knowledge about transformations, or if you wanted to find the points of intersection by brute force, you could set x plus 1 equal to x squared minus 1. So you get x squared, 0 equals x squared minus x minus 2. That factors. So you get x equals to 2, x equals to -1. So that would be at 2. So that means we're going to be integrating from -1 to 2. So each of these integrals that represents volume, we're going to be integrating on the interval from -1 to 2 because these are all going to be perpendicular cross sections. And those cross sections will all have a base or a side length, depending on what the shape of the cross section is, that we'll refer to as S of x. And S of x we can determine by top minus bottom, right? Since we are integrating with respect to x, we have vertical slices. So top, x plus 1 minus bottom, x squared minus 1. That will simplify to be -x squared plus x plus 2. Okay. So if the cross section is squares, I think it's sometimes helpful to draw a little picture. That's not required. Okay, so the base is S of x. All the other sides will also be S of x. And the area of a square, right, would then end up being S of x squared. And that's what we're integrating. So we're going to find the volume, we would be integrating from -1 to 2, -x squared plus x plus 2 squared dx. Okay, for rectangles, cross sections that are rectangles that have a height of 2, drawing a rectangle, okay, where the side would be the base, S of x, but it would have a height of 2. That means that the area will be 2 of the rectangle, will be 2 times S of x. So that's what we're integrating to find the volume. So volume would be from -1 to 2, 2 times -x squared plus x plus 2 dx, right? 2 times S of x. And then rectangles that have a height 5 times the base. Okay, well, if the base is S of x, the height would be 5 times S of x. That's a 5. Therefore, the area would be 5 times S of x squared. So volume would be equal to the integral from -1 to 2 of 5 times -x squared plus x plus 2 squared dx. Quarter circles. So quarter circles would look something like that, where the base is S of x. And area of a circle is pi r squared. So area of a quarter circle would be pi r squared divided by 4. And in this case, r, the radius of the circle, is equal to S of x. S of x is the base, corresponds to the radius. So our volume be the integral from -1 to 2 of pi over 4 times negative x squared plus x plus 2 squared dx. Okay, when the cross sections are semicircles, so half circles, the base being s of x. So then our area would be pi r squared divided by 2. And again, r is equal to s of x. So our volume would be the integral from -1 to 2 of pi over 2 times negative x squared plus x plus 2 squared dx. And where the cross sections are isosceles right triangles. So that means that the legs are equal in length. And then the base is one of the legs, so not the hypotenuse. So the base is s of x. That means that the height is also s of x, right triangle. So the area would be 1/2 base times height. So in this case, it would be 1/2 times s of x squared. So volume would be the integral from -1 to 2 of 1/2 times negative x squared plus x plus 2 squared dx. And you guys know how to integrate all of these by hand. Ooh, some of them would be yucky to have to multiply out, or using your calculator. Okay, where the cross sections are isosceles right triangles, but the hypotenuse is the base. So think about taking that right triangle from before and rotating it, but now s of x is going to be the hypotenuse. Okay, we don't know what the legs would be. They would be dependent on whatever the hypotenuse is. But we do know, because this is an isosceles right triangle, that this angle would be 45 degrees, this angle would be 45 degrees. And we need the height in order to determine the area, right? Area equals 1/2 base times height. The base would be s of x. The height we could determine because, well, we're trying to find h. We know that that line that we dropped to represent the height cuts s of x in half. So this right triangle that we've created with the height and half of the hypotenuse, so that leg would be s of x over 2. So we could say, okay, well, for sides of this right triangle, opposite over adjacent, tangent of 45 degrees is equal to h over s of x over 2. And tangent of 45 degrees is equal to 1. So that means that h is equal to s of x over 2. And the area would be 1/2 base, which is s of x, times the height, which would be s of x over 2, or 1/2 times s of x. So the volume will be the integral from -1 to 2 of 1/4 times s of x squared, or negative x squared plus x plus 2 squared dx. And then last one, if the cross sections are equilateral triangles. Okay, so if the side lengths of the triangles are equal, meaning each side would end up being a length of s of x. Okay, now we need the area. So we are going to need the height. We have the base is s of x, but we are going to need the height. Because this is an equilateral triangle, you know that all the angles are 60 degrees. So this angle would be 60 degrees. And then we can go, okay, well, opposite over hypotenuse. That's sine of 60 degrees would be h over s of x. Sine of 60 degrees is root 3 over 2. So h would be equal to root 3 over 2 times s of x. So the area of each equilateral triangle would be 1/2 base times height. So that would end up being root 3 over 4 times s of x squared. So the volume of the solid that's generated would be the integral from -1 to 2 of root 3 over 4 times -x squared plus x plus 2 squared dx. Okay, and then for our last couple examples, I have a couple past free response questions. So from the 2013 exam, we are given, so this is no calculator. And I kind of like the no calculator ones of these because you just end up, for the volumes, you a lot of times just end up having to set up the integral that represents the volume. But our region that we are given that is bounded by the graphs of f and r. Sorry, f and g. The graphs of f and g. But it doesn't label which one is f and which one is g. You have to use your pre-calc knowledge in order to determine which is f and which is g. Okay, so looking at this, well, f is a parabola that opens up. So that would have to be the bottom function here. And then cosine starts high, right? And it's been vertically stretched by 4. So this top function has to be g of x. Okay. And then we can see their points of intersection. That's nice, right? That's at, oh, why did I just do that? I didn't mean to do that. That's at 0, 4. This would be at 0, 4. And this would be at 2, 0. Okay, so first question, a little bit of a review from section 7.1. Find the area of R. So the area of R would be the integral from 0 to 2, being x intervals, top function minus bottom function. So g of x minus f of x. Okay, and you can write in the rules. You would be expected to integrate this. I know you guys know how to integrate this. You would need to do a u substitution to integrate g of x. But you should end up with 16 over pi minus 4/3. Okay, part B, getting into the volumes questions. Write, but do not evaluate. That's great. An integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals to 4. Horizontal line y equals to 4. Okay, rotating about the horizontal line, that means that this region, okay, rotating around, there is going to be a gap, meaning that our cross sections, which will be perpendicular to y equals to 4, meaning vertical slices, vertical cross sections, we're setting up an integral that is with respect to x, that means. And we are using washer method, because that region R is not completely flush against y equals 4. When we rotate it around, we're going to need to think about subtracting some volume, right, in the middle. Or think about each cross section is going to be a washer. Okay, so our volume would be pi, don't forget pi, times the integral from 0 to 2, thinking x values, of big R squared minus little r squared, not to be confused with the region's name. So big R squared minus little r squared. Okay, big R, remember I suggest labeling big R, little r. Big R, little r. Right, for radius of rotation. So big R, top minus bottom, that's going to be 4 minus f of x, or you can write in what f of x is equal to, squared, minus little r. Little r would be 4 minus g of x, and then squared, dx. Okay, so that represents the volume. Okay, part C. Region R is the base of a solid. For this solid, each cross section is perpendicular to the x-axis and is a square. Okay, so square cross sections. Right, but do not evaluate an integral expression that gives the volume of the solid. So we need to know what the base of each square will be, and that will be s of x. We are given that the cross sections are perpendicular to the x-axis, so vertical cross sections. So s of x will be equal to top minus bottom. What is that? G of x minus f of x. And then we know that the area of the square, so each side of the square is s of x, right? The area is going to be s of x times s of x, or s of x squared. So our volume will be the integral from 0 to 2 of g of x minus f of x squared. Since they have defined what g of x and f of x is. You could write in the like 2x squared minus 6x plus 4 and 4 times cosine of pi over 4 times x. You can write that in, but since we're not even evaluating the integral, this also represents it. Okay, last one, calculator active. Calculator active. Okay, so you could pause the video and give this one a try on your own, and then check your answers. Could have done that with the other ones too. But let R be the region enclosed by the graph of x to the fourth, f of x equals x to the fourth minus 2.3 x cubed plus 4, and the horizontal line y equals to 4. Well, it's obvious which is the horizontal line and which is f of x. But they have so kindly labeled what region R is. Okay, so this would be y equals to 4. And then this is f of x. Okay, so we need the volume of the solid generated when R is rotated about the horizontal line y equals to -2. Okay, well, y equals to -2 is down here. All right, y equals to -2 is down here. Rotating around y equals to -2. So that means we're going to have vertical slices, meaning our integral that represents the volume will be with respect to x. So volume of R, you guys be specific, is equal to pi. If we think about rotating R around y equals to 2, there's going to be a gap. This is washer method. Okay, so pi times, we need the limits of integration. So we need all of the x values, so the smallest x value and the largest x value over which R is enclosed, bounded. So you could do this with, it is calculator active, and you could find the points of intersection using your calculator, but this one is actually easy enough. Not intersection. That you could set 4 equal to x to the 4th minus 2.3 x cubed plus 4, right? And then that turns into, you could factor out the cubed, those 4's canceled, and you would be left with x cubed times x minus 2.3. So x equals to 0 and x equals to 2.3. Right, so this would be 2.3. So we are integrating from 0 to 2.3, and then we need big R and little r, not to be confused with region R. So big R, little r, big R, little r. Okay. So big R, top minus bottom, will be 4 minus negative 2 squared. And then for little r, top minus bottom, that'll be f of x. I'm going to write it out here since we are going to be typing it into our calculator. Minus negative 2 squared dx. Okay, could add one more set of grouping symbols there. And then you are typing that into your calculator, and they will accept 98.868 or 98.867 is what the rubric said they would accept. Question B. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Okay, so that means that the base of each right triangle can be found top minus bottom, right? S of x, the base of each triangle, will be 4 minus f of x. So 4 minus f of x being x to the 4th minus 2.3 x cubed plus 4. So that means that the 4's will cancel and s of x will be negative x to the 4th plus 2.3 x cubed. Okay, so then thinking about, that's not a square, thinking about those right triangles, right, which have a base of s of x, a height of s of x as well, because they are isosceles right triangles. So the area will be 1/2 base times height. So 1/2 times s of x squared, meaning that the volume will be equal to the integral from 0 to 2.3 of 1/2 times s of x squared. So negative x to the 4th plus 2.3 3.3x cubed squared dx. And then when you put that into your calculator, they will accept 3.574 or 3.573. Part C tricked me at first. Vertical line, x equals to k, divides R into two regions with equal areas. Write but do not solve an equation involving integral expressions whose solution gives the value of k. Okay, so you're trying to determine, I'm going to erase this other stuff just so we could focus on the picture. Yeah, it's fine. Okay, so we are basically trying to figure out where would we want to draw a vertical line, x equals to k, that would divide the area of R in half. Well, the area of R would be the integral from 0 to 2.3 of top minus bottom, right? Of top function minus bottom function. That's y equals to 4. So of 4 minus f of x. We would want to figure out what we would want to integrate to that is on that interval. So from 0 to k, so that that value of 4 minus f of x, so basically we would be saying, okay, well, this area would be equal to 0 to k of 4 minus f of x. And then this area would be from k to 2.3, also 4 minus f of x. And those areas should be equal to each other. So we can actually just set that up and state that those two integrals should be equal to each other. Okay, because it says, write but do not solve an equation involving the integral expressions whose solution gives the value of k. So that would be 0 to k of 4 minus f of x dx. It's up to you if you want to substitute f of x in there. Would be equal to the integral from k to 2.3 of 4 minus f of x dx. Now, I will tell you, all right, I slipped into the common mistake here. I'm going to write it in red as a do not do. Does not work. And I'll explain why. I was like, oh, well, we just want to figure out what k would be so that if we were to add up those two integrals that I just wrote, right, 0 to k of 4 minus f of x dx plus the integral from k to 2.3 of 4 minus f of x. Well, that should be the integral from 0 to 2.3, right, of 4 minus f of x, which would represent the area of region R, right? This is the area of region R. However, this statement is true for all values of k that are on that interval. And, right, because it's just a property of integrals. It doesn't actually give us an equation that we can solve. It's just, it's true for all values of a k. you would earn 1 point. I think this is a 2-point question. You would earn 1 point for representing the area of one region, right? So like representing that, but you would not receive both points for this question. So this doesn't work, okay? It's true for all K. Whereas this would not be. This is like saying the area on that's one integral describes minus the area that the other integral describes is equal to 0. Okay, and that is it for 7.2.